All right, so welcome to our guest speaker. We are live on YouTube, and the participant team from CUB will now do the introduction.
We can't share our screen right now.
I can stop sharing.
Thank you, sorry about that.
No problem.
Are you seeing this fine?
Yes, we can see it.
Awesome. Okay. Today, we are elated to have the honor of introducing Dr. Victoria Hamilton from the Southwest Research Institute. Dr. Vicky Hamilton is a planetary geologist at the Southwest Research Institute in Boulder, Colorado, and a co-investigator on the OSIRIS-REX and Lucy missions. She spent most of her time living in Colorado and Arizona, and outside of researching what is on the surface of other planets, you can find Dr. Hamilton hiking and snowshoeing in the Rocky Mountains, taking photos of landscape and extreme close-ups of wildflowers, and taking up archery. A quote from Carl Sagan that best describes her work is, "Somewhere, something incredible is waiting to be known."
Dr. Hamilton was always interested in space science. She was greatly intrigued by Carl Sagan's Cosmos and the Voyager missions. However, at school, she didn't think that she would be pursuing a career in planetary science. She excelled in subjects like English and social studies, but it was her decision to take a geology class out of curiosity while a junior at the Occidental College that put science on her radar. Finally, a summer internship at JPL, at the end of which she asked, "Can I stay?" sealed her passion for geology of other planets. She also did her graduate school at the Arizona State University.
Briefly about some research conducted by Dr. Hamilton. In her own words, she describes her research as understanding the spectral features of minerals and rocks in the visible, near-infrared, and thermo-infrared portions of the electromagnetic spectrum, and using this knowledge to identify and/or characterize the rocks and minerals on planetary surfaces. As we introduced earlier, Dr. Hamilton is the co-investigator on the OSIRIS-REX mission, a asteroid study and sample return mission to the carbonaceous near-Earth asteroid Bennu, and is also the co-investigator for Lucy, which is a space probe that will visit a main belt asteroid and 6 Jupiter Trojan asteroids to hopefully reveal the quote-unquote fossils of planet formation.
And without further ado, let's welcome Dr. Victoria Hamilton.
Oh, thank you all very much. Thank you for having me here. That's a lovely introduction. I appreciate it so much. Let me go ahead and share my presentation with you. And I'm going to leave it in this mode just so that I can see all of you a little bit better. So what I'm going to talk about today, when we get into the nitty-gritty of it, is the composition of asteroid Bennu and what we might predict about the sample that the OSIRIS-REX mission is presently on its way back to Earth, having collected at this asteroid. And partway through, I'm going to encourage all of you to participate with me in a little bit of data analysis. All you need is eyeballs. And so hopefully that will be interesting and a little bit of fun. So before I jump into that, you've actually already heard a little bit about how I became a planetary scientist. This is certainly not something I ever expected to do as a kid. I never grew up wanting to be a scientist or study planets. I had a general curiosity and interest about space, like a lot of kids do. I had general curiosity and interest in rocks, like a lot of kids do. But as you heard, it wasn't until I got into college and I took an elective science class in geology that I really got interested in science. I was not somebody who was sort of classically interested or, very, very good at things like physics or chemistry or biology. But geology really struck a nerve with me because it was something I could literally walk out my door and see all around me. And I learned how mountains form and how streams formed and why there are different kinds of streams, or even that there are different kinds of streams. So that's what got me into the sciences in the first place. And then it wasn't until I did this internship at the Jet Propulsion Laboratory in Los Angeles that I really appreciated planetary science as a way to take geology and do something really, really exciting with it. And so when I was there, I was an intern on a mission called Magellan, which was a NASA mission to Venus. The image at the lower right is a perspective view created from radar images of the surface of Venus and made a 3D image using the topography data that we had. And so really what excited me was that, you know, the mission was an active NASA mission. It was returning new pictures every single day. And many days, I was one of the first few people on Earth to actually see those images. And the idea that this could be something I got to do every day of my life was just really compelling to me. So that's when I decided that I did want to go ahead and get an advanced degree. So I got my PhD after that. And so I've been really fortunate to work on several NASA missions. After Magellan, I worked on a mission called Mars Global Surveyor, which was an orbiter in orbit around Mars. It's no longer functioning, but I did some of my work on that. There's also a mission called the 2001 Mars Odyssey. That is also an orbiting spacecraft. It is still there. It launched in 2001, and it's still going strong 20 years later. It's a great success. And two of the images returned by Mars Odyssey are the two on the left on the screen here in the middle of the slide, the day IR and the night IR. Those are two pictures taken by an instrument that I work on called Themis. And it's an infrared imager, so it's showing you what temperatures basically things have at the day and the night. And then the color image below that, the really gaudy colors, that is a map of mineral composition on the surface of Mars. And so all those round features that you can see there are impact craters. And then you'll see these sort of diagonal lines. Those are fractures in the surface of Mars. I also spent some time working on the Mars Science Laboratory. That was the first rover, big rover that landed on Mars back in 2012 called Curiosity. Her sister rover, Perseverance, has just landed on Mars back in February. So I got to participate on a rover mission. We'll talk about OSIRIS-REX today, and then you heard a little bit about Lucy, which is going to launch in October, and will visit a main belt asteroid and several Jupiter Trojan asteroids. And so in addition to the work I do on spacecraft missions, I also have a lab here at my business. I'm at home today, obviously, but I do have a lab at work, and I particularly use that to study meteorites. And so we'll talk about how all of those things kind of come together today. So now you know a little bit about me. Let's talk a little bit about OSIRIS-REX and what it is. So the name OSIRIS-REX is an abbreviation basically for a much longer name: Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. Most of that makes sense. Regolith may be a new word for some of you. Regolith is just the uppermost surface on a planet, on either, it could be the moon, it could be Mars, it could be an asteroid. We don't call it soil or dirt because on Earth that implies that there's like bits of vegetation and things as part of that. And so on planetary surfaces, we use a term that you know doesn't imply that. And so regolith is what that word is. So the acronym OSIRIS-REX is obviously a lot easier to say than that big long mouthful of a name. The point of the mission is to really explore primitive asteroids, and asteroids are really time capsules to what was going on in the very, very earliest years of our solar system. So we had, you know, before we had what we have today as this sun and solar system, there was a solar nebula. And early in that process, we formed asteroids. A lot of asteroids ended up getting incorporated into the planets, but a lot of them didn't. And what's great about having those is that they basically got frozen in time. And that's well over 4.5 billion years ago. So by getting frozen in time, they were essentially little recorders of what was happening in the solar system, what was the chemistry of the solar system at that point in time. And everything that happened later to, for example, the planets are very geologically active. They have continued to evolve over geologic time, just like the Earth has. And so a lot of that early record has been destroyed or modified. And we wanted to get a sample of unmodified material. So the primary objective of this mission, first and foremost, above everything else, was to collect a piece of one of these very primitive, very old asteroids and bring it back. And we wanted it to remain pristine in doing that. So we developed a system that we believed would be capable of collecting at least 60 grams of material. Now, I don't know about all of you. I don't think well in grams or even ounces, but a good analog for how much material 60 grams is about 30 sugar packets. So if you think about the sugar packets that are on the restaurant table, take 30 of those, and that's the amount of material we're trying to bring back from this asteroid. Now, while we're at the asteroid, we have this spacecraft and it's got scientific instruments on it. And so we use those instruments to map what the asteroid's made out of, which is what we'll talk about primarily today. But we also use it to map out the geology of the asteroid, its topography, and try to understand its physical properties as well, because we want context for the sample that we bring back. Another goal of the mission is to provide ground truth or verification for interpretations that scientists make from ground-based telescopes. So depending on where you are, where you have been, you may know that there are big telescopes on the top of Mauna Kea in Hawaii. There was, until unfortunately very recently, a radar telescope called Arecibo in Puerto Rico. There are other locations where we have telescopes around the world that we use to understand other planetary bodies and asteroids, but we can't really verify that our interpretations are 100% correct until we actually go to one of these places and collect close-up data or even samples. So we're going to help verify that what we think we know from telescopes is actually accurate. Now, there's an image on the right here that hopefully you've been kind of staring at while I've been blabbing. And this is what we call a shape model of Bennu. It's not a photograph of Bennu. It's not an image, but it is our best estimate of the shape of the asteroid Bennu based on telescopic observations. Now, this is a pretty small asteroid as asteroids go. Asteroids can range in size from anywhere from a meter or two all the way up to thousands of kilometers in size, asteroids like Vesta or Ceres. But most asteroids kind of are in the hundreds of meters to hundreds of kilometers size. Bennu is kind of at the lower end of that range. It's only about a half a kilometer in size. We can think of it as roughly spherical. For reference, there's images there of the Empire State Building and the Eiffel Tower. And then just for reference, I've also put the sizes in feet. And then just to give you yet another way of referencing this to something you might know, a 10-story building is about 100 feet high. The Empire State Building, if you go to the top level where there's actually a story that you can get out of an elevator on, the Empire State Building is just over 100 stories. The upper part of it is all the tower. So that gives you a sense of just how small this object really is compared to the size of the Earth, for example. There's some interesting factoids here about Bennu. I won't go over these in great detail, but Bennu spins very rapidly. Its day is only about 4 hours of our time, but it takes Bennu longer to go around the sun in a year than it takes us. So it takes about 437 Earth days for Bennu to go around the sun instead of the 365 days that it takes us. It's not a very dense object, and its average albedo is another word for its brightness. It's a very, very dark object. And so we had to design our instruments to work in those conditions. So one of the things I mentioned here on the slide is that we wanted to return and analyze a sample of a pristine asteroid, but I didn't actually use the word carbonaceous yet. There are different kinds of asteroids that we know are made out of different things, and we wanted one of these carbonaceous asteroids as our target. So the question is, what does carbonaceous mean, and why do we want samples of it? So meteorites come in different flavors based on what they're made out of and some of their geologic history. And so there's a group called carbonaceous chondrites. They have a lot of carbon in them compared to other meteorites. It's only a few percent, but that's more than most other meteorites have. And then these are stony meteorites. And so if you know anything about meteorites, or even if you don't, you might know that some meteorites are stony, so they don't have a lot of metal in them. They look just like ordinary rocks for the most part. Whereas you have their ranging meteorites that range from stony iron, and all the way to iron, where if you cut an iron meteorite open, it is completely full of metal. And so you may have seen pictures of iron meteorites that have been cut, and they have this beautiful patterning on them that can be etched out. That is a characteristic of the iron grains in it. But we're looking at these carbonaceous ones, and these are some of the most primitive meteorites that we know about. But even these, even though they're these time capsules of what was happening 4.567 billion years ago, they've still experienced a little bit of geologic processing. So some of them have been exposed to water, and then some of them have been exposed to heat. And it depends on what their parent body was. And a parent body is just to say meteorites come from some other object, and that is called the parent body. And you can just think of that as an asteroid. That's what it is. I don't know how many of you may have had a geology course. I don't assume anybody has, but I'll use some words and try to introduce them to you. So these meteorites are comprised of different kinds of minerals. Some of these minerals are called silicates. Some are called oxides, some are called carbonates, others are called sulfides. And then we also have organic compounds. So the image on the right here shows you one of these meteorites, a meteorite called Orgay. And this particular meteorite has been exposed to a lot of water. It's been altered by water. And that has made it very fragile. And hopefully you can kind of deduce that just by looking at this picture. You see all the crumbly bits down around the bottom of the meteorite on the table. That's because this is a very fragile rock, not to mention that it's over 4 billion years old. Now, the minerals that actually make up that rock, examples of some of them are shown there at the bottom as samples from the earth. So I mentioned that you have minerals called silicates. Silicate refers to the fact that they have a dominant component of silicon in them as an element in the chemistry. The two minerals on the left there at the bottom, olivine and serpentine, are both examples of silicate minerals. Olivine is something you may actually have encountered and not know it. If any of you, I believe it's a December birthstone, is peridot. Peridot is olivine. It is exactly what is in that picture right there. Serpentine is a mineral that forms when you add water to olivine. There's water locked up in that mineral, even though you can't see it because it looks like a rock. Magnetite is what we call an oxide mineral. So it's primarily made up of oxygen with some other elements attached to it. And then the sulfide is primarily made up of sulfur with, again, some other elements attached to it. And we'll look at that in another way in just a minute. But one of the things that's really interesting is, as I said, some of these meteorites have been, as asteroids, exposed to water. So they contain a good record of water from the early solar system. Now, you might be wondering by now, well, if we have all of these meteorites and they're such great resources, why do we need to go get a sample? Well, part of the problem is that meteorites are a biased sampling. So when you're doing a scientific experiment, you probably know that you want to do a study that accurately represents a range of conditions. Meteorites, we have no control over the meteorites that actually land on Earth. And so we can't ensure that we have a representative sampling of all of the asteroids that are out there in the solar system. And in fact, we know that some of the meteorites, like Orgay, are actually underrepresented in our museum collections and in the samples we've recovered, in part because they are so fragile. They commonly burn up in our atmosphere on their way in. And so meteorites like Orgueil are quite rare. In addition to that, of course, when a meteorite comes through our atmosphere and lands on the Earth, and then we go collect it, it's already contaminated. It's gone through our atmosphere, it's landed on the ground, it's come into contact with our biology on Earth, it's come into contact with Earth chemistry. And even if we go get a meteorite within hours of its falling, there's still scientific measurements that are compromised because there is contamination from the Earth environment. So that's why we actually wanted to go get a sample and bring it back where we could control what that meteorite was exposed to, or what that sample of asteroid was exposed to. Now, before we go to the OSIRIS-REX mission and how we collected the sample, what I thought I would do is talk to you a little bit about the technique I use to understand the composition of asteroids and other planetary surfaces, and that's spectroscopy. And so this is basically just a way of measuring the light that is reflected off of a surface or emitted by a surface. That can be the moon, Mars, Bennu. We do spectroscopy on the Earth using satellites and aircraft. So really what we're looking at is how much light is reflected or emitted from a surface as a function of wavelength. And that is essentially a fingerprint for composition, for what it's made out of. And so just to put this in some context, I'm showing the electromagnetic spectrum on the left here. I'm sure at this point, most of you are quite familiar with this. You know that at the short wavelengths, we have very high energy light, high energy wavelengths. They're so small and so energetic that is dangerous to human tissue, which is why, you don't want to get a whole lot of x-rays in your life or a whole lot of imaging work done, because those waves, while they're good at penetrating and looking inside of us, they also can cause damage to our tissue because they're so energetic. As you move to longer wavelengths across the middle here, you get to this small part of the spectrum that is the visible, that our eyes can see. We can do spectroscopy here with scientific instruments, but your eyeballs are doing spectroscopy all the time because you are looking out into the world around you and seeing different colors. And oftentimes those colors are indicative of what something is made out of, whether that's a rock or food or something else. If it's a metal, your brain is doing spectroscopy all the time. Beyond the part of the wavelength range that our eyes can see is the infrared, and that's what we're going to talk about today. This is the zone that I work in on a daily basis, but beyond that, you have longer wavelengths like microwaves and then radio waves, which we use for communication. So the OSIRIS-REX mission actually carries 2 spectrometers for doing spectroscopy. I'm only going to talk about one today. One covers the visible and near infrared part of the spectrum, so about 0.4 to 4.3 microns. But what I'll talk about today and work with you on is thermal infrared spectroscopy. So now we're talking about 6 to 100 microns. And if you've ever seen an infrared imager like a FLIR, what we're looking at those wavelengths is thermal infrared. But what you're doing is you're seeing it over a big broad band of that region rather than as very discrete wavelengths. So let's introduce what that looks like. All right, so here are examples of minerals. So as I said, mineral groups have different chemistries that we refer to as by the dominant elemental composition of the minerals. So there's a group here called silicates. Silicate minerals are dominantly composed of silicon and oxygen, but they can have other elements added to them as cations. So some of you, I'm going to assume, are familiar with those terms. Quartz is a very, very common mineral. Probably almost all of you know exactly what quartz is and what it looks like. There's a picture over here at the top of quartz crystals. I'm sure you've seen those somewhere. Quartz is pure silicon dioxide. Olivine is another mineral. That's the one I said a moment or two ago was peridote, the green birthstone. Olivine is also based on silicon and oxygen, but it has iron and magnesium in it as well as part of its chemical formula. Now, the spectrum on the top in blue at right there is labeled as quartz, but it's there just as a representation of a silicate mineral. And so what we're looking at here, I would say focus on the top axis here for a unit that you'll probably relate to better. So this is the wavelength in microns. So the shorter wavelengths are here on the left, and it gets longer as we go to the right. And then what we're plotting that against is something called emissivity. And this quantity, what emissivity is, almost doesn't matter for what we're trying to do today. The point here is that you have sort of a flat line along here from about 6 microns all the way out to about 8 microns. And then all of a sudden it takes a dive here, and you get this, this big, what we call absorption band between about 8 and 10 microns. This band can move around, and it changes its shape depending on whether you're actually looking at quartz or olivine or a different silicate. There are a few other absorptions scattered around. There's a big group out here between about 17 and 25 or 30 microns. And that's also common to silicate minerals. Now, if we go to the next group over here, the next bullet down is the carbonates. And carbonates are carbon and oxygen based, and they can have, again, other cations attached to them like calcium. In that case, we call a carbonate mineral calcite. And the spectrum of calcite is shown here in red. And so you'll notice that this mineral now, rather than having silicon oxygen as its fundamental unit, it's got carbon oxygen as its fundamental unit. And the positions of these absorption bands has changed. So now there's a big absorption band over here where quartz didn't have one. Where quartz does have an absorption band, calcite does not. And that's because the positions of these bands are related strongly to whether it's a silicon oxygen mineral or a carbon oxygen mineral. So there's another big band out here in the red spectrum around, between 25 and 50 microns. That's also a diagnostic feature. One of the things I want to point out before I forget is that when you are going to identify a mineral on another planet and you're comparing to spectra like this that we've collected in the lab, you don't want to identify just one feature. You want to identify all of them. If you're going to identify quartz and you see a shape like this between 8 and 10 microns, you better see a shape like this out around 20 microns. Because if you see one but not the other, then you may not have correctly identified the mineral. Okay, let's move on to the third one, and that's the oxides and hydroxides. So again, these are minerals that are based fundamentally on just oxygen or oxygen and hydrogen. So hematite is an example of this. This is an iron oxide. And hematite you can think of as rust. When you grind up hematite very, very finely and it gets exposed to air, it turns red. That is rust, iron oxide. Magnetite is also an iron oxide, but its chemical formula differs. So we give it a different name as a mineral, and we call it magnetite. And in this case, it's because this particular form of iron oxide is actually magnetic. The spectrum of magnetite is shown over here in the green at the bottom. And then the thing to notice here again is that these minerals don't have carbon oxygen bonds, so they don't have these big carbon oxygen related bands. It doesn't have silicon oxygen bonds, so it doesn't have these big bands related to the positions of, or that are positioned based on the fact that silicon and oxygen are the primary units here. In this case, you just have your cation and oxygen. And so you don't see a feature here, you don't see a feature over here, but you have these two little bands out at the longest wavelengths. Now, we're going to actually use this plot to help us make some interpretations about meteorites and about the surface of Bennu. But one point I want to make is that meteorites are going to be a little more complicated looking than this, because when you have a meteorite or a rock, those are made up of more than one mineral. And each of these spectra here are just a single mineral. So when they're combined, you combine the spectral signatures as well. And I'll show you an example of how that works in just a minute. But first, before we do that, I want to involve you guys here now. And so get ready to raise your Zoom hands, because what I want to have you do is take a look at the plot on the right, which is the same one we just talked about. I've kind of grayed out the far side of the image because the plot on the left doesn't cover those wavelengths. But what I want you to do is look at the plot on the left and look at all of those spectra. Those are all spectra of meteorites. And then compare that to the 3 spectra on the right. What do you think is the primary mineral group that makes up these meteorites, just based on comparing? Ivan?
Yeah, so to me, it seems like it's silicate. It's the primary group
Okay.
because it gives the biggest jump. Like the form of the lines on the left is most similar to its form.
Okay. Anybody else make any observations about the spectra? Erin?
I agree that it looks most reminiscent of silicate, but I do notice that the dip seems to be shifted almost, so it's not quite as between 8 and 10 as I think you'd probably like it to be.
That's a great observation. That's a great observation. Okay. And I apologize if I mispronounce your name, Chinmay? Chinmay?
Yeah, I was gonna mention that too, but even like the dip.
Oh, you went mute.
Sorry, yeah. So the dip that you see in the images to the left is kind of similar to the dip for carbonates, except then you don't see the kind of steep like collapse that you see at around 10 microns. So it doesn't seem to exactly match like either 3 of them. So it may be like a combination of
Okay.
carbonates
right.
and silicates.
All right. Ivan, we're back to you.
Yeah, I also noticed that towards the end, the graphs on the left are like inclined downwards.
Mhm.
And this kind of corresponds to the oxide graph. So maybe it has to do something with that.
Okay. All right. These are all great observations. And so you're doing exactly what I do for a living. And the answer is that, in fact, they are dominated by silicates, but there are other minerals there. So let me walk you through this the way I would walk through it. So if we're looking here, let's start at the bottom. So if we look at the oxide spectrum at in the wavelength range that we're showing in these plots, the oxide has virtually no absorptions from the left-hand side all the way out to where that little sort of tooth is. There's just no real absorptions out there. So we can tell that the meteorites don't look like that. They've got these big bands out here, whether they're from, between 9 and 15 or 9 and 12 or, wherever they are. We know that those big bands are not oxide bands. So oxide is not the dominant thing that's here. The comment about the carbonate band, that was a good one. There are some wiggles out here by the names of the meteorites, but again, the actual position of this big feature matters. So this feature kind of starts a little bit longward of 6¼ microns and probably goes out to 7½ and it's this big dip. So if we look out here on the left chart between 6 and 7½ there's nothing like that out here. So although there actually is some carbonate in these rocks, it's only 1 or 2% in most cases. And so you really don't see it very well in the spectrum. So that means that carbonates are at least not the dominant phase in these, or dominant mineral in these meteorites. The observation that the quartz silicate spectrum here is between 8 and 10, where the band minimum is somewhere around here between probably 8 and 9, is offset from what we see over here. That was a really good observation. And if we had more time, and I actually have some other slides that I could bring up later to show you this, it turns out that silicates, this band position slides around to the left and the right a bit, depending on exactly what the cations are. So in this case, it's just silicon and oxygen. But if I were to start adding other cations like calcium and sodium and iron and magnesium, these bands would start to shift a little bit to the right. And that's what's happening in the meteorites. The meteorites are not made out of quartz, which is why they don't look like quartz, but the band positions are telling us that a silicate mineral is what is the dominant phase here. So you guys have done a great job. So now I mentioned a few minutes ago that minerals are mixtures when they are in rocks or in meteorites. And so the spectrum of a rock or a meteorite, it adds linearly the components of that rock or meteorite, which is very, very convenient for me because it means it's much easier to interpret the spectrum of a mixture when you know that the things that are in that mixture add linearly. So I've got some simulated spectra on the left. I've labeled them band 1 and band 2 at the top. Another way to think about those is just mineral 1 and mineral 2. It doesn't matter what minerals they are. These are just fake curves that I generated on the computer. And so band 1 is centered around 10 microns. Band 2 is centered around 13 or 14 microns, and it's much smaller than band 1. Now, if I add those together in equivalent portions, so 50% of one and 50% of the other gives me 100% of a mixture. And when you do that and you mix them in equal proportions, you see that band 1 remains strong and deep and band 2 is there, but it's still smaller. And then you can see that when you add them in the middle, you get a little hump. So you get a little extra curve in there. But now I can say, okay, if I know there's two components, I can probably mathematically separate this out into the two things above it. Now, if I mix them in different proportions, if I make band 1 or mineral 1 a smaller proportion of the mixture, it's only 25%, as opposed to band 2 or mineral 2 being 75% of the mixture. Now, band 2 is going to look much stronger than band 1 because it's actually more of what is there. And so we use this knowledge to help us understand mixtures on asteroids or on Mars or on the moon and figure out what they're made out of and how much of each thing is there. On the right is an example using mineral and rock spectra. So plagioclase is the name of a mineral. Augite is a different mineral. It doesn't matter for our purposes what they actually are, but they do have two different compositions. They're both silicates. One has a lot of calcium and sodium in it, the plagioclase does, and then the augite has a lot of iron and magnesium in it. But when you mix these two minerals together in the right proportions, you make a rock that a geologist would call a gabbro. And when you mix their spectra together in the proper proportions, you get the spectrum of a gabbro. And so this is, how mixing works in the world of spectroscopy. Now, we use this so that, again, like I said, we can go to a place like Bennu or Mars or the moon and carry an infrared spectrometer, and we can make measurements of mixtures, and then we can unravel what the components of those mixtures are. I'm not going to talk too much more about this concept today, but I wanted you to have an understanding of why the meteorite spectra don't look like the pure mineral spectra that I was showing you. So now we can dive in a little bit to Bennu, and we're going to do our deduction experiment again in a minute. But before we do that, I want to show you what Bennu looked like when we first rolled up on it, which was not at all what we expected. The image on the left is actually going to be a little movie that I'll start in a moment. It is what we call approach images. So the spacecraft was still somewhat far away. I think we were still well over, I think we're around 1,000 kilometers away when this picture was taken. And it shows Bennu. And you can see now, compared to that, if you think back to that shape model that I showed you in comparison to the Eiffel Tower and the Empire State Building, that looked very smooth because it was just the shape. This is actually what Bennu looks like. And then when we got even closer, we got pictures like the one on the right. And that really scared us because we did not think Bennu was going to be that rocky. Now, just lower left of center, I'm hoping you guys can see my cursor. There's this sort of bright white or brighter, I should say, rock. That's about 27 feet across. So it's huge. This is an enormous rock. If you were standing down in here, it would dwarf you. It's almost 3 stories tall. And this is what the whole surface of Bennu looks like. And this is why we were so scared, because our spacecraft wasn't designed to sample this kind of stuff. So we had to worry about that. And we'll come back to that thought in a minute. But what I want to do next is talk about what all this stuff is made out of. So we pulled out our spectrometers, we started collecting data, and now we're back to spectra again for a minute. So we've got our three friends over here, our silicate, our carbonate, and our oxide. And then these are two spectra of the surface of Bennu. These are the two different types of spectra that we saw when we looked at Bennu. And I'm just calling them surface type 1 and surface type 2, just to not give them names that imply anything about what they are, what they're made out of. But you can see that these are a little more complicated looking than what we saw with the meteorites. And so here's again your opportunity. Take a look at where the band positions are and how many of them there are. And then let's talk about what you think they might be made out of. Anybody want to take a guess? Erin.
In this case, it almost looks like maybe both silicate and carbonate are present.
Okay. Ivan?
Yeah, I also agree with Erin, and it seems like there is a lot of silicate because the graph is like stretched down. That's what I
Okay.
noticed.
Okay. Anybody else want to make any observations? Okay. Like I said, this is a little bit more of a complicated situation. We'll start with the simple part first. If you just look at everything to the right of about 9 microns, ignore what's on the left of that for a minute. You see this big dip here between about 9 and 15 microns, and then there's a similar one, but it's shaped a little bit differently in the red spectrum. And then you see that there's a big absorption in both spectra out beyond about 20 microns. So in fact, that is telling us that there's a lot of silicates present. So we've got, again, it doesn't go as far to the left as 8 microns like it does here on the reference plot. But that again is because the chemistry is a little bit different. But we also have these longer wavelength bands as well. Now, the oxide, again, doesn't seem to be a dominant component here. We'll come back to that in a minute. And then there is the idea that maybe there's some carbonate here. And that's presumably because you're seeing this big dip here. Things are not straight across at the top. And we'll come back to that again in just a minute. But this is actually a peculiarity of measuring a real planetary surface. The spectra over here on the right are nice crystals of minerals that have been measured in a lab. They're nice and clean. They're solid samples. They don't have any dust on them or anything like that. It turns out that when if you go out in the real world, you go up onto a rock, you're climbing around, you might notice that the surface of the rock has dirt and dust on it. The same thing happens on planetary surfaces. And that dust and dirt causes funny things to happen in the spectrum. And so some of the spectral shape out here is actually due to the presence of dust on the rocks on Bennu. It does look like there's an absorption out here, but in fact, there isn't. It's only because of the dust that this is happening. But you've made good observations, and you would be able to identify, carbonate potentially by looking for a couple of other things. You've got one very, very sharp, narrow band here between 850 and 900 wave numbers. I shouldn't use wave numbers, kind of closer out here to 12 microns. You don't see that strong, narrow band out here. Even though this dips down, there's nothing quite like this out there. And then at the farthest end, you'll see that beyond 25 microns, there's a really big spectral absorption out here in the red spectrum on the carbonate. And it doesn't look quite the same with the other one here. So again, carbonates we think are present, but again, at very, very small abundances. So let's do another experiment, another question. So now we're looking at the same two Bennu spectra on the left, and now I've changed out the plot on the right to go back to our meteorites. So now we've got meteorites, and we know that these meteorites are, well, we think these are the kinds of meteorites that we went to Bennu to find. And so now the meteorites here are plotted in a specific order. The meteorites up at the top are the meteorites that have interacted a lot with water. And so their chemistry has changed from what they used to be after this interaction with water. And then as you go down the plot, these are meteorites at the bottom that have actually gotten heated up. And when they got heated, they were heated so much that they started recrystallizing and formed new minerals. So that's why the spectral features in their details look very different. All of these, again, you guys already figured out that most of these are all dominated by silicate minerals, but they're different silicate minerals. So now you can see how spectral shapes change as the minerals in the rock change. Now, if we look at these guys and compare to the Bennu spectra, what do we see? How do we compare those? And which ones do you think might be the best matches? And let's start with surface type 1. So does anybody like a particular meteorite on the right as something that looks the most like surface type 1? Yeah, Ivan.
I would have guessed it's somewhere in between MIL09 something and ALH. Maybe I'm more inclined towards MIL, I think.
Okay. And why? What made you think that?
Well, MIL has the most distinct first peak, like at least
Okay.
has some sort of a peak. And then general shape is quite similar, plus it has two peaks which are almost on the same level each other and kind of resemble. Then they go down in the end. It makes sense. I guess that's
Okay.
Yeah.
Okay, those are good observations. Chinmay?
I would say surface type 1 like most resembles CM1/2. I'm trying to look at, like, for example, at around 9 microns, we see that the emissivity goes down by a large amount, and then kind of bottoms out at around like somewhere between 10 and 11, which matches the emissivity graph on the left. And then for finally we see it like go down severely at around 20 or slightly before 20 microns. So that's like my final, I guess, clue.
Okay, all right. Umran, did I say that right?
Yeah, that's right. I think it's most similar to CI1 because in addition to like all the things Chinmay said, unlike CM102, I don't think it has a very like a pronounced dip at around 15 microns. It's more like a straighter line, I suppose, like CI1.
Like out here between 15 and 20?
Yeah.
Okay.
And yeah, just in addition to like all the dips at like 10 microns and approximately between 20 and 25, I think the amount of dip also matters. For example, like CI1 has a more pronounced dip than the other meteorites, which I think matches more closely with surface type 1.
Okay. All right. Erin?
I think ultimately I agree that it's CI1 because at first I was looking more at the shapes of the dips, but I noticed that it has that feature at around 20 wavelengths that it seems to correspond really well with the one that we're trying to match. And I think overall its shape seems to fit with that.
Okay. All right. And Esh, is that correct?
Ish. Yeah.
Ish. Sorry.
It's all right. I think it's ALH 83-100 because I noticed that there is a bit of a rise around 9, around the wavelength of 9. And it rises first and then it falls down into the peak. And even around 15, around 16 or 17, there's a short dip, which is also noticeable in the surface type 1. So I think that's one. These are two factors that I'm interested in.
Okay. Jay?
My initial thought was that it was most like MIL because there was a fairly pronounced dip at around 9 microns, and then it seemed to be around the top of a peak that flattened out just a little bit at around 15 microns. But Erin pointed out the feature on the 20 micron point that looked a lot like, I'm not sure what it's called, but the very first measurement that's in the red line.
Or
So I think
gay.
it could be,
It's French.
I see. Thank you. I think it could be closer to that one. Those were my two main observations.
Okay. You guys are great. You guys are scientists. You're all, you have all just deduced basically what we published 2 years ago when we got these spectra. So in fact, I'll say that again, that there's this bit of a trick here, which is that this drop off between or this slope in the Bennu spectra between 8 and 9 microns is due to the fact that there's dust on the surface. So you didn't do anything wrong if you looked at that slope, but unfortunately the spectra on the right don't have that characteristic. So in this particular case, that's a bit of a red herring. But seeing that the peak here around 9 is at that particular position is a diagnostic feature. And so that is a little more similar to a couple of these things up here, including ALH 83-100. And I'll explain in just a second how these meteorites get their names. So it's very similar to that. So a couple of you observed that was similar. That's a great observation. You looked at, it kind of dropped down very rapidly there with a minimum around 10 microns. And that's exactly where the minimum in the surface type 1 is. And then you all started to make some really good observations about what's going on at the longer wavelengths too. Somebody observed that, it's kind of flat here in surface type 1, which is a little more like Orgay than it is like Allen. This is ALH means Allen Hills. Again, I'll explain it in a minute. So Allen Hills has this very deep band here that none of the meteorite or the Bennu spectra have. And that was actually a mystery to us for a little while. But importantly, this long wavelength feature between 20 and 25 microns is in fact most similar in type 1 to these top 2 spectra. And so for those of you who, a couple of you thought MIL, which is Miller range, was an analog. It has some distinct similarities in this particular band here around 10 microns. But where it differs is when you look out here at the really long wavelengths. And so it drops off here at more like about 17 microns instead of 20. So that actually is meaningful. That's a meaningful difference. And then instead of just having this sort of one V-shaped band out here like the top 2 spectra do, the MIL spectrum has a very different shape, and that too is also significant. So that's why MIL is not as good of an analog. I'll go ahead and just talk you through type 2. The surface type 2, I said there's a bit of a trick here. Surface type 2, we don't think is actually chemically different than type 1. We think it's got more dust. And in fact, this whole shape change out here around 12 to 15 microns, we think is attributable to dust. It's making the spectrum look funny because the light scatters differently off of dust than it does off of rock. So there's no spectrum on the right that would represent surface type 2. But what you can tell, dust is, how do I put this in the easiest way? Dust will affect the shorter wavelengths more than it affects the longer wavelengths. So when you look out here at these 2 spectra, they look very, very similar past about 15 microns. And that's how we deduced that, in fact, the compositions were similar and that this change here in the red spectrum was just due to the presence of dust. So, but you guys did a great job making the observations and connecting these surface types to specific meteorites. So let's go one step further. There is also an oxide mineral in these spectra. And so what I've done here is I've drawn a couple of vertical lines, one around like 18 microns, one around somewhere around 20, I don't know where that is, 30, 35 microns. These 2 vertical dotted lines actually highlight the 2 small features in the Bennu spectra that I know are attributable to an oxide mineral. So what I've plotted on the right are a whole series of oxide minerals. and I forgot to put the names on. Sorry. But if anybody wants to take a guess at which mineral is present and just tell me whether it's the third, fourth, fifth down, or by color, if it's red or purple or whatever, somebody have a guess at, not a guess, an educated, informed analysis of which oxide mineral that might be. Yeah, Erin.
I think it might potentially be the third one down, the kind of tealish one, because you pointed out only two dips, and it seems to have one distinctly after 25 microns, which is one of the places where you pointed out.
Absolutely right. And that is from our very original plot. That's our oxide spectrum. That's magnetite. And so we think there's magnetite on the surface of Bennu, probably at maybe the 5% level, 10% level. That's why it's kind of weak in these spectra, because again, if you think back to that mixing example I gave you, the bands, you know, when it's a small proportion of the mixture, the bands can be smaller and weaker. That's what's happening here. But yes, this was also one of the very first things we observed about these spectra was we saw these two features and we knew that they looked like magnetite that we'd seen in the lab. All right, that's great. You guys have done a great job. Thank you for participating. So why does this matter? So you've learned, you've deduced for yourselves that the Bennu spectra look like these meteorites, and you deduced that in fact they look most like the spectra of meteorites that have had interactions with water. And this was exactly the kind of sample we went to Bennu to collect. It's what we wanted. Now, based on comparing to those meteorite analogs, we can predict what the sample we collected will contain in it. Even though there was no exact match in that group of spectra, and we have many more that we've compared to, but we never found an exact match. But we know that they're close enough that we suspect the sample will be dominated by silicate minerals, particularly the ones that contain water. We know that there's at least this one oxide mineral, the magnetite. And then because we know what's in the meteorites, we can predict that the Bennu sample is also going to contain some organic material, some organic compounds, some carbonates, and some sulfides. And in fact, the other spectrometer that I haven't talked about did make measurements of Bennu that actually show signatures of organics and carbonates. It's a little easier to detect them at the shorter wavelengths sometime. So, you know, we've gone through all of this. You've just deduced what Bennu is made out of and what we're bringing back. And so hopefully you're wondering like, okay, well, how do we actually do that? How do we collect a sample and bring it back? So let's talk about that. So I showed you the pictures of what Bennu looked like when we first got there, and we all just kind of thought, oh my God, how are we ever going to collect a sample on a surface that looks like that? So we didn't have a lot of options. Most of Bennu looks like this just incredibly rocky place, but we managed to find 4 locations that we thought had enough clear space around them that we would be able to collect a sample. And so those are the 4 sites that you see here. And they've been given different names that are related to birds. And we ended up selecting the one in the top left called Nightingale as our primary sampling site. And that is in fact where we did sample Bennu. I need to explain a little bit about how we sample Bennu. And that is that this spacecraft doesn't actually land on the asteroid ever. It has a big long arm on it. And the arm has a sampling mechanism at the end of it. And so what we do, if you literally think about like putting your arm out in front of you and having a big grabbing sample handler on the end of it, you can touch the asteroid, grab your sample, and then back away without ever actually landing on the surface. And that's what we did. So we selected Nightingale. We were a little worried about this big giant rock over here to the right. But we were able to maneuver the spacecraft around it, and we actually successfully sampled at this Nightingale site back in October. Now I'll show you how the mechanism works. So now this will be a little animation in just a moment. So what you're looking at is a side view of the surface of Bennu. I mean, obviously not the actual surface of Bennu, but a graphical representation of the side of the surface of Bennu at the bottom. And then this is the side view of the sampling mechanism coming down onto the surface of Bennu. So at the top of the image is where the sampling head is connected to the arm. And then if you were to go straight up out of this, that arm would go up eventually to the spacecraft. Now, the way this works is that we contact the surface, we fire jets of air into the surface, it disrupts the rocks on the surface and causes them to go into the sample container. So I'm just going to let this loop several times so that you can see this. So the air comes down, disrupts, it flows into this containment area on the outside of this big ring. So this sampling head thing, it's a big ring. And there are these little flaps here that allow the sample material to go in, but are supposed to keep it from flowing back out here at the end. All right, so that's how this works. And this device is called a touch and go sample acquisition mechanism. And so we just call it TAG-SAM for short. Now, here's what it looks like from the perspective of the spacecraft. TAG is what we call the sampling event, touch and go. So again, we're not landing, we're touching and we're backing up and getting out as fast as we can, because this is a dangerous environment for a spacecraft. So what you're doing now, if you imagine, me standing here with my arm stuck out in front of me, the arm is coming from me, I'm the spacecraft. It's kind of hard to see that it's an arm because all that black stuff is black blanketing around the joints of the arm. And then you can see the sampling head is that big round white thing out there at the far end. So this is another video, and now I'm going to start it, and you're going to see what the spacecraft saw when we actually sampled Bennu. So it's an amazingly dramatic event. And if you remember, asteroids are airless bodies. There's no atmosphere here. So when you touch it, stuff just goes everywhere. There's no air to slow it down. It just literally exploded around us. And that's all sort of real time play. So this happens very, very quickly. And we back away from the object as fast as we can. It turned out that we did in fact get dust and dirt on our cameras, on our instruments, because of this event. So stuff, dust, and everything came blowing back at us. And you can think of it as, like if you're a camera sitting on a spacecraft, you just got a bunch of stuff, sand blown in your eyes, and it sticks on the lenses and stuff. So we saw that after the TAG event. So I'll play that through one more time. I just love this. This is just so cool. Now, here is what we looked at after we did this sampling event. So what we can do is we normally, we would approach the asteroid with the arm out and the sampling head out to touch the asteroid and sample it. But we can also turn that sampling head around and look at the bottom of it. And that's what the picture on the left is showing you. So this is the bottom of the sampling head. These bigger silver circles around the ring, oops, didn't mean to move it, are actually stainless steel Velcro pads. They're meant to be able to collect up little tiny grains of sand off the surface of Bennu, just to get the uppermost surface of the object instead of the disrupted stuff that goes up inside this inner ring to get collected in the outer part of the ring. Now, what you'll also notice here, this is an animation too. This is just 3 different frames. So if you take an object, like there's a particle, I'll put my cursor over where it starts, and then it starts moving up to the left, like it wants to go out of the frame. You'll notice if you look at any one of these things, these are particles. These are pieces of Bennu that are actually radiating away. They're traveling away from the sampling head. If you look inside the sampling head, you'll notice there's this wavy line between dark and light on the left-hand side. That's that mylar flap that was supposed to come back closed. We actually collected so much sample that the mylar flap couldn't close. And what was happening, we realized at this point in time, was that particles were actually drifting away out of the sampling head. And so that got us really scared. We had plans to do some other experiments with the arm before we put it away for storage for return to Earth. But we saw this and we realized that if we kept going this way, we could actually lose a whole lot of sample that we didn't want to lose. So we actually talked to people way high up the food chain at NASA and said, we don't want to do these other experiments. We want to put this thing away right now. Can we have your permission to do that? And NASA said yes. So what you see over on the right is in the middle of the image, you can hopefully maybe recognize there the side view of the sampling head. It's this silver sphere with the little perforations in it. And at the top of it is the joint where it's attached to the arm. And then the arm kind of goes up and to the right there. And the arm is placing the sampling head into a capsule, the sample return capsule. So the bottom of the capsule is this sort of reddish area. And then it's got a lid, and the lid is on the left-hand side of the image. It's popped up, and the arm disconnects from the sampling head. This lid folds closed, and now you have this nice little capsule that's sitting on the body of the spacecraft. And the spacecraft in May left Bennu and is now on its way back to the Earth. So here's my last slide talking about what that process is going to look like. So the spacecraft is going to fly back to the Earth now. It will get here in about September, early September of 2023. And when it comes close enough to the Earth, it will release the capsule. So the graphic on the far left here shows you the spacecraft. The two big squares are the solar panels that power the spacecraft. And you can see that little white capsule that's meant to show it being ejected off the spacecraft, being released from the body of the spacecraft. The next panel over is, again, an artist's rendition of what that capsule will look like as it's coming through our atmosphere. It will be coming in at a very high rate of speed. It will be very hot, but we have a protective surface there that will allow it to survive that re-entry. And then the other sort of high level view is, again, another artist rendition of what that capsule will look like as it's coming in through the atmosphere. And then as it gets closer to the surface of the Earth and slows down, it will pop out a parachute, which will slow it even further. And then in the last panel at the lower right, what you'll see is that capsule sitting on the ground. And the place it's going to land is in Utah. There's a test and training range out there, a military facility, but it's an enormously huge area of desert that makes it a very safe place to return an object from space, makes a very easy place to go find something that's returning from outer space. And so we'll pick up that capsule. We'll put the capsule on an airplane. We'll fly it to Johnson Space Center in Texas, which is where the meteorites are kept. And we will open and examine the contents there under very, very carefully controlled conditions so that we don't contaminate the sample. And then once we catalog the sample and understand exactly what we've got and how much we collected, scientists will then be able to get pieces of that collection of sample, take it to their labs and analyze it for any kind of measurements they want to do. And so I will be coming back and getting sample and bringing it back to my lab and collecting more spectra of what the Bennu spectrum looks to compare to how that Bennu spectrum looked. So that is still happening. This mission will go on for quite some time. And from that, I'm happy to address any questions you have, offer you some places where you can go to keep track of what OSIRIS-REX is doing. And yeah, I'm happy to answer any questions that you might have. And I know I said I would tell you about meteorite names. Let me go back to that for just a second. Let me move that out of the way. Meteorites, the way they're named, if they are observed to fall or are found in a particular, well, they're given names based on where they are found is the first thing. Oftentimes it is the name of a location with the nearest post office. So Orgay is a location, Murchison's a location, Allende, Vigorano, those names are location names. We also find meteorites in Antarctica. Antarctica is a fabulous place to find meteorites because Antarctica, so much of it is covered in ice and snow. If you're zooming around out on the ice sheet and you see a big black rock sitting on the top of the ice and there's no mountains around, it pretty much had to fall out of the sky. And so we go collect a lot of meteorites in Antarctica. And we name them based on a geographic location. So ALH is the Allen Hills. MIL is the Miller Range, which is referring to a mountain range. There are some other ones like Elephant Moraine. And then the number tells you what year it was found and what number that year. So 83100 means it was found in 1983, and it was the 100th sample that the team collected that year. MIL 090001 is a Miller Range sample collected in 2009, and it was the first sample they collected. It's got an extra 0 because they collected more than 1,000 samples that year. So that's how the meteorites actually get their names. So, okay, with that, I will just stop talking for a minute and let you guys ask me questions about Bennu, about science, about me, about whatever you want.
Thank you so much for a wonderful talk. We have been collecting questions off screen on a document, and your work has definitely inspired a lot of curiosity. So I'm going to just jump into those.
Okay.
Our first question is, how common are different sizes of asteroids, and what makes an asteroid spherical versus any other shape?
Those are great questions. To the first one, the size distribution of asteroids, there tend to be, well, we don't actually have the greatest accounting of sizes and size distribution. We know certain properties go along with certain sizes. So smaller asteroids like Bennu tend to be relatively free. Even though I talked about there being dust on Bennu, it's a very, very thin layer of dust, a few microns thick. Just like, you know, what you would get in your house if you didn't dust for a week. Other asteroids have a lot of dust, big pools of dust, and that tends to occur when they're larger. What we don't have a good handle on is the small ones can be hard to detect because they're small. So when you've got a telescope and you're looking out into space, you're going to see the biggest stuff the most easily. We don't know how entirely how common the smallest ones are. The biggest of the big ones like Vesta and Ceres tend to also be rare. So most of them fall, you know, most of the ones we know about and can catalog fall in sort of the tens of meters to hundreds of meters or kilometers in size. That's not a really great answer, but it's the one I've got. The second question, remind me what it was.
Sure, it was, what makes an asteroid spherical versus any other shape?
Right, okay, so that is another excellent question. So some asteroids have very, very irregular shapes. Bennu is like, you know, a lot of them are sort of like, there was a mission that visited an asteroid called Eros. Eros looks like a big potato. It looks like, you know, you could pull a baking potato out of a bag, and that's what Eros looks like. It's because these objects sort of, they sort of coalesce from many smaller pieces in the very beginning. And some of them form by very slow impacts. So you might have had two smaller objects that kind of ran into each other at such low speeds that they didn't break, they just kind of got glommed together. So that's part of the reason they're not normal shaped. Bennu is a little unusual in being roughly circular. We kind of call it top shaped because it's a little more diamond shaped. Some of that shape, we think that equatorial rim or ring that it has, let me go back here so you can kind of see how it's wider at the equator. We think some of that is actually due to the fact that it does rotate so quickly. So I said the day on Bennu is only about 4.3 Earth hours long. So it's spinning very, very quickly. And so to some degree, we think that that shape is partly because of the forces that are being applied as the asteroid spins. So it depends on size. It depends somewhat on what it's made out of. It depends somewhat on how it formed. So there's multiple things that lead to asteroids having different shapes.
Thank you. Our next question is, in what ways does going through our atmosphere change a meteorite?
Okay, so when the meteorite goes through the atmosphere, the main change that occurs to it is all on the outside. So asteroids, before they become meteorites, while they're still floating around out in space, are at space temperatures. They're incredibly, incredibly cold. Going through the atmosphere, of course, frictionally heats the exterior of the meteorite. It doesn't, because it happens quickly within, a matter of seconds or a couple of minutes is the most time the meteorite spends in the atmosphere. The outside melts quite commonly, but not the inside. So you get what is called a fusion crust. So it's, if you slice the rock in half after you pick it up, there will be this very, very thin rind around the outside where the rock melted. But if you could cut open that meteorite right there in the field, you would find that the interior is still very, very cold. So it's only that outermost part that gets changed in the atmosphere, and it's heating and melting that happens. But by the time it lands on the Earth, it's already resolidified. It's already effectively refrozen. And so you can walk out and you could literally watch a meteorite fall and then walk over and pick it up, and you'd be able to do that.
Hi, thank you. Our next question is, why is Bennu so rocky, and why did you not expect it to be?
Very good questions. So we know from looking at telescopic data that smaller asteroids like Bennu tend to be very fast rotators. So again, this idea that Bennu's day is only 4 hours long is related to the fact that it's a small asteroid. Small asteroids tend to rotate quickly. Bigger asteroids tend to rotate more slowly. That's not universally true, but it's common. Because it's rotating quite quickly, the smaller ones, they do tend to fling off the smallest loose particles. So that's one reason that Bennu is rocky. The reason we didn't expect it is a very different story, and it's a very interesting one in terms of how one approaches science. So there's a property called thermal inertia. And what it means is, how quickly does a rock absorb heat, and then how efficiently can it release that heat, re-emit that heat? And so I'll give you an example that I think most people can relate to. You've undoubtedly been to a beach somewhere, whether it's on a lake or on a beach, ocean beach. And during the midday hours, at the peak heating of the day, you really don't generally want to stand in sand in your bare feet because the sand is incredibly hot. The sidewalk, on the other hand, is actually potentially cooler than the sand. So you wouldn't mind standing on a sidewalk in your bare feet midday at the beach, but you don't want to stand on the sand. So the sand has what we call low thermal inertia. It's very quick to absorb daytime heat and warm up. The sidewalk has high thermal inertia. It's hard to get it to warm up very quickly with that heat. At night, the reverse is true. The sand will cool off very quickly, but the sidewalk stays warm longer. So if you're out at night on the beach, the sand is usually quite cold, but the sidewalk is still warm. So we use this daytime, nighttime change of temperature, both how much it changes and how rapidly it changes, to understand the properties of planetary surfaces. So we do this on Mars a lot, and Mars is kind of where a lot of this work was pioneered. And so you look at the daytime and nighttime temperatures of the surface of Mars in different places, and you see that some places have high thermal inertia and some places have low thermal inertia. And we use that to make an inference about what is on the surface. In the case where it's high thermal inertia, we think there's more rocks because they're slow to heat up and slow to release their heat. Where there's low thermal inertia, we think it's mostly sand because it's easy to soak up heat and then easy to release it. We had telescopic data of Bennu that suggested that the majority of the surface had a thermal inertia that told us it was mostly made up of things like from sand grains to, a couple of centimeters in size, mostly small rocks and pebbles. And the telescopic observations were just that. They're telescopic. So you don't actually see the different areas on the surface. You just get one measurement for all of Bennu. So that was our interpretation. But when you make that interpretation, you have to make some assumptions about the properties of the rock you're dealing with, like what is its density? How efficiently does it conduct heat? And it turns out that when we got here and we saw this, we realized that some of those assumptions were very much wrong. That we had assumed that Bennu would have rocks with densities that are similar to Earth rocks or Mars rocks. But if we come back up here, I'll point this line out here, where the mean density of Bennu is only a little bit more than the mean density of water ice, which is a density of about 1 gram per cubic centimeter. Most of Earth's crustal rocks, any rock that you would walk out and find, has a density somewhere around 3. So when we made an error in assuming the density for these calculations, it made our calculations mislead us into thinking that for a high density rock, the thermal inertia told us it was small particles, when in fact, if we had properly calculated or used the density closer to 1, we would have gotten a much better estimate and realized that Bennu was a lot rockier than we thought. So this was a case where the mission helped us make sure, I said down here that we wanted to compare to ground-based observations. Well, now we know a potential error that we might make with our ground-based observations. And so we don't have to make those errors again.
Thank you. Now that we have more data, it's really interesting how telling thermal inertia can be.
It's a neat thing to study.
Yeah, it really seems like it. Somebody asks, on slide 10, you said that there are some peculiarities in the graph due to various factors such as dust. This made it look like there's a peak at that wavelength. How does someone distinguish between an actual peak and a peculiarity?
Again, a very, very good question. The short answer is practice. This is the kind of stuff that I learned about when I went to graduate school. I started with things like the plot on the right, which is nice, pure minerals. They're nice and clean. They're chemically pure. You take a bunch of spectra of minerals like this and you learn what they look like. And then you grind it up into a powder and you take a spectrum of that. And then you realize that it looks different. And you have to, you just learn through time what the difference between a solid and a powder can look like. And then just with experience, just like you gain experience with anything. I mean, it's like if you like to go mountain biking, the very first time you went mountain biking, you probably weren't going off of huge jumps. But as you get practice and you get familiar, you get more comfortable doing those kinds of things and judging the situation. The same thing is true here. You become experienced at looking at these things. And I can now, after many years of experience, look at a bunch of spectra and be like, oh, there's dust, there's not dust, there's carbonate, there's not carbonate. You're seeing a weird effect due to contamination here, but not there. So it really is just experience. I mean, I've probably analyzed at this point in my career between laboratory spectra. I mean, I've analyzed hundreds of thousands of laboratory spectra and probably as many or more spectra of places like Mars and Bennu. And so when you just see things over and over and you see the subtle variations that can occur, you just learn what they are over time. But part of the learning process is reading the scientific literature. Scientists communicate primarily through writing, believe it or not. We write papers and publish them in professional journals, and that's how we communicate what we know to other scientists. And so I went and did, and still do, a lot of reading about what other scientists are learning. And then we, develop new questions, and we go back into the lab and make a new measurement and, try to figure out, well, why is that happening? And under what conditions does it happen? And so we build up our knowledge that way too.
Thank you so much. Our next question is, why don't you want to land on the asteroid to sample it?
It was mostly because actually developing a spacecraft that can land on a surface takes more technological effort. It's harder. And we thought that this approach, by having the arm, was sufficient to collect the sample we needed. Given what we learned about the surface of Bennu and how it looked, it turned out that was actually a really good decision, because if we'd had to land, it might have been even harder to do that safely. So in this case, we didn't need to land, so we didn't.
Thank you. Next question is there software used to determine the mineral composition of an asteroid, or is it all done manually? How are you sure that you're right?
Oh, go ahead. Sorry, finish.
Yeah. How are you sure that you're right, and how are you able to get exact percentages?
Again, very, very good question. So the way it goes back to these plots. I'm trying to think, do I have another? Maybe I do, maybe I don't. All right, I'll come back to that in a second. No, I guess I didn't do one. Really? Oh, here we go. All right, here, let's look at this. I think I need to share a new thing. All right, so here's another plot. Let me make that bigger so you can see it. Okay, so yes, we do use software for this. I don't know if any of you at this point will have been familiar with or know about linear algebra, but linear algebra works, is how we do this. We take what we call the unknown spectrum, which is the spectrum of the mixture. It could be a rock I picked up out in the field. It could be a meteorite, whatever. I take the spectrum of that bulk rock, and I get my spectrum that has all the different components contributing to it. What we do is we take that spectrum, we plug it into an algorithm. The algorithm reads in a file that contains a whole library of reference spectra. And then what it does is it basically mathematically inverts the mixture spectrum, and it says, okay, which of the spectra out of this library do I need to have, and at what abundances to reproduce this unknown spectrum? And so it goes through and it does its math, and it says, okay, I think you're going to need these 4 minerals to reproduce this spectrum, and here's the abundance of each one you need to do it. So the plot here is showing in black, the solid black line is the measurement of a rock. The dotted gray line on top of it is the modeled spectrum that comes out of the algorithm. And one of the ways we validate the result is we do what we call plot the residual spectrum. So we either just subtract or divide the measured by the modeled to see where there's deviations. So this residual line has just been offset. The fact that it's at 0.75 is meaningless. Normally it would plot around 0. So if the model was a perfect representation of the unknown, there would be an absolutely flat line at 0 for the residual, because you've modeled everything perfectly. So I've just offset it so that I can put it on the same plot. But what you see there are actually a series of little wiggles, and those little wiggles are showing you the exact positions where the model doesn't perfectly replicate the unknown. I will tell you, just again from experience, this is a very good model. This example shows you when things are working well and working right, this is what you get out. The math also returns uncertainties on the calculation, so we can use that. to guess at, or to assess, I shouldn't say guess at, to assess how accurate the model results are. So that is how we do it. So I might get a bunch of Bennu spectra and I can plug them through this algorithm, and then the algorithm goes and for every single spectrum compares to the library and says, this spectrum is made up of these things at these fractions. This next spectrum is made up of these things at different set of fractions, and so on. So that is how we do that. There's still a fair amount of manual stuff that we do too, I should say, because when we first saw Bennu and saw those two surface types, some of the things we'll do, we'll just create very simple spectral parameters and say, oh, there's a slope of this quantity here. I can just calculate that slope for every spectrum and I can make a map of that. And I can, very easily deduce what are some of the changes across the globe of Bennu before I even get to the phase of doing this. So it's a combination of both algorithms and manual analysis.
That's incredible. Thank you. Our next question is, how is it decided what experiments are performed given that the samples of asteroid material are limited, and who gets to work with these samples and why?
You guys are asking fantastic questions. So yes, given that, we're only getting 30 sugar packets back, we think we got more than that. That's good. A large fraction of the material, probably more than half, will immediately get put into secure storage. It will never get analyzed by anybody on our team or in the community, the science community right now. It is much like the samples the Apollo astronauts returned. It gets put away for future generations because we know that 100 years from now, there's going to be scientific instrumentation that we can't even imagine today. And so we want to preserve a lot of the sample for 100, 200, 300 years from now, when there will be other newer ways to understand what those samples are telling us. So part of the sample goes away to storage right away. In this particular case, the way things will work is because the mission, the NASA mission team did all the work to go collect this sample, bring it back, and all of that. There are the scientists on the team will be the first people to analyze the samples. So, boy, how many of us are there? There's probably 60 or 70 people on the science team who are part of the sample analysis team. And we all have different specialties. So, I do infrared spectroscopy, so I will get a sample and I will be responsible for doing that part of the analysis. Somebody else who studies oxygen isotopes is going to get a sample and they're going to go measure the oxygen isotopes. Another person is going to go do electron microprobe analysis or X-ray CT scans or whatever. So the team is made up of people with different specialties, and we will all get a little bit of the sample material to do our analyses. And then we all come back together and say, okay, well, here's what my analysis showed. What does your analysis show? Do they agree? Sometimes they can't agree because they're so different kinds of analyses. They tell you about different things. And so that will happen. And the science team will get first crack at the samples for the first year or two. After that, then what happens is the remaining available sample goes into what we call curation. It's like what a museum does. They curate things. Johnson Space Center will curate the samples, and scientists in the community will write application letters to say, I would like a piece of the sample. Here's how much I want. Here's what I'm going to use it for. And then there's a committee of scientists who will say, okay, yes, we approve this request, and then we send them the sample. So that's how it works. And the same thing happens with Antarctic meteorites. They're collected by the US government through the National Science Foundation and NASA. They get collected and curated at Johnson. Again, you write a letter that says, I'd like to get a piece of this particular meteorite that you collected. Here's what I'm going to do with it. And then they send the sample to you. So that's how that process works.
I was not aware that of the storing of like data for future generations. It's very interesting and considerate as well. Our next question is, can you name a meteorite after yourself? If you find a meteorite, can you keep it for yourself?
Well, if you're out wandering around and you find a meteorite, it is absolutely yours. Presuming if you're on somebody else's private property, you need to ask them before you take it. But if you happen to be just out wandering around in your own backyard and you find a meteorite, that is your meteorite. You may sell it, you may hold it, you may donate it to a museum. You can do anything you want with it. Yeah, so that's how that works. You cannot name them after yourself. There are rules about how meteorites get named. And so they have some fascinating names depending on where they're found. There's a meteorite I work on that was found in the Sudan. It was actually seen to fall. It was actually the only time that astronomers saw an asteroid that was, I guess, I want to say it was maybe 12, 18 meters in size. They saw it coming and they were able to collect a very limited amount of data about the asteroid before the asteroid entered the atmosphere. And then there are pictures you can see of this thing streaking through the sky. And then afterwards, there's like these dusty clouds that hover in the sky because the dust particles, hung around. But the meteorite landed in the Sudan, and the people who went and collected it had to name it after the nearest, I don't think there was a post office, there was a train station nearby. This is out in the absolute middle of nowhere, African desert of Sudan. And so they named it after the nearest station, which was Al-Mahada Sitta. And so you get some incredibly crazy meteorite names based on place locations around the world that are really funny. But no, you can't name them after yourself, unfortunately. You can get asteroids named after you, however, and I have one named after me. A lot of people do. You can't do it yourself, but somebody can nominate you to have that happen, and that's a lot easier.
That's neat. So next question is, could the spectrum of two minerals add up to look like the one of a different mineral? And if so, how can you differentiate between them?
You guys are asking such incredibly good questions. Let me come back over here for a minute. So this is similar to what I showed you before, where I was showing you different mineral groups, so silicates. Here I've just got a few more examples of mineral names. But the thing that distinguishes one mineral from another is one of two things or both. First and foremost, it's usually chemistry. A mineral has a definite chemical formula. So that's what I've shown here. Quartz is SiO2. Pyroxene is a different silicate, iron or magnesium iron silicate. Plagioclase is a mineral with sodium aluminum silicate. So the chemistry changes, that defines a different one mineral from another. But another thing that differentiates them is the structural arrangement of the elements in the material. So let me pop over to this. So on the left here, this is a representation of silicon, is the little tiny blue dot in the middle, and then the four sort of whatever color that is, peachy colored spheres are oxygens. So this is SiO4, okay? It can, inside the mineral structure, you can have this SiO4, and then the you get many of these SiO4s, and they're linked to each other through cations, through another element like magnesium or iron or calcium. When these little SiO4 units don't touch each other directly, they're considered to be isolated from each other within the structure. On the other hand, you can get these little SiO4 groups connected to each other and linked. And when they link in the form of a chain, we call that a chain mineral or a chain silicate, okay? You can have two chains that are attached to each other, and then you've got other elements around them, and that's a double chain. That is a different structure of minerals. So you can have a mineral that has magnesium and silicon and oxygen, and it's a magnesium silicate, and if it has just single chains, that's one mineral. But you can have the exact same elements and have double chains, And that makes it a new mineral because the structure of it is different. How it's assembled is different. So you can imagine then that this becomes more and more complicated and doesn't just grow in 2 dimensions, it can grow in 3 dimensions. And so you can have very, very complicated mineral structures. So the way we identify minerals in the first place is by chemistry and structure. Because they differ in chemistry and structure, they will all interact with light differently. And so now the chart on the right here is showing you there's our buddy quartz up at the top. And now these are all silicates. And you'll notice that the band positions, we were talking when we were looking at the meteorites and comparing to the silicate, carbonate and oxide, you guys were noticing that the bands weren't quite in the same positions as they were in quartz. This is why, because the different minerals have different chemistries, different structures. That means they have different spectra. And while they're broadly similar in detail, they are quite different. So the answer to the question is no 2 minerals have the same spectrum. And so you don't have to worry that by combining 2, you will make the spectrum of a 3rd. So that is actually something that we're very fortunate to be able to leverage. We don't have to worry about that kind of confusion. And now you've had your mineralogy lesson for the day.
Thank you. It's incredible how nuanced spectroscopy is.
It's incredibly powerful.
Mm-hmm. Our next question is, how does the presence of water in an asteroid give clues about its origin and its journey into the inner solar system?
Okay. This is sort of a broad ranging area. One of the things we'd like to understand is, we're all here. Life, we exist. We are made up of water and organics. So those are the 2 most important compounds to life as we understand it. And so the idea is we want to understand, what was the original inventory of organics and water? We know what we have today, and we have the asteroids and the meteorites that tell us what happened 4.5 billion years ago. But there's sort of this big gap in the middle of how did we go from no life, but water and organics to all of a sudden people. So we want to understand what was the abundance of water. We want to understand what was the chemistry of the water. So you may be familiar with the fact that water can be in the form of, of deuterium, for example. So we want to understand the proportions of the different types of water that we had and use that to try to piece together what might have been reasonable evolutionary pathways from how we got from there to here. How the water tells us about the migration into the inner solar system, that gets beyond that's a subject that I'm not actually an expert in, so I won't go too far with that because I don't want to misinform you. But yeah, there is an idea that these particular types of meteorites that we're talking about, because they have so much water in them, probably formed in a part of the solar system that was far enough away from the early sun that it was quite cold. Water was stable, but probably in the form of something more like a slush. Not exactly ice, not exactly water, although it probably varies with distance from the sun, just as you might expect. The closer you are to the sun, the warmer you are, the more likely you are to be more liquid water. You get too close, you boil away all that water. But yeah, there are hypotheses out there about where asteroids formed and how they've migrated in and out towards the sun. And so we can address those kinds of questions. I'm not the expert in how we do that, though. So I'll have to find you another scientist to answer that question.
Wow, all that info from just water. Our next question is, why are different wavelengths affected differently by dust?
Okay, so the way to think about this is that if I'm a 5 micron wavelength of light, okay, I'm way off the left of this chart here somewhere. I have a very small wavelength. If I intersect a big slab of rock, that big slab of rock is much, much bigger than I am. If, however, I encounter a 5-micron dust particle. Now that dust particle is the same size as me. What happens is you get funny scattering. That's the term, the term in physics is scattering. What happens is, if I'm this little wavelength and I'm coming in on this big slab, I kind of hit the slab and I bounce off of it, and I don't really see too far inside that slab. But if I'm a 5-micron wavelength of light and I encounter a 5-micron dust particle, all of a sudden it's the same size I am. And so I can like go through it and get refracted, or I can get reflected. Funny things start to happen when the size of the geology is the size of the wavelength of light. So dust tends to occur at certain sizes, and those sizes tend to be a few tens of microns or less. So if the dust has, like, let's just call it an average size of 8 microns, then you're going to see interference at 8 microns, but a 50 micron wavelength of light is much bigger. And so it's going to kind of not see that dust. It's going to go right past it and not even notice it. So that's what we call wavelength dependency. And so with small particles, you see it most at the smallest wavelengths, and then you don't see it as much at the longer wavelengths. I hope that makes some sense. It's one of the more complicated things you have to learn about how this works.
Thank you. Another question is, how is your mission different from the Japanese Hayabusa 2 sample return mission?
Good question. So the Japanese have run 2 missions, Hayabusa and Hayabusa 2. Hayabusa 2 just went to an asteroid very much like Bennu. In fact, when we were selecting the asteroid we were going to visit, Ryugu was originally one of our possible targets, but we knew the Japanese were considering it and they chose it. And so we said, okay, we're going to go somewhere different. Ryugu looks a lot like Bennu. It's about half again as big. It's bigger than Bennu, but it also is incredibly rocky. Their mission differs from ours because they carried a different set of scientific instruments, and they also sampled the surface of Ryugu in a very, very different sort of way than we did, where we had this big circular sample collector on the end of an arm. They basically had sort of a thing that looked like, it kind of worked on the principle of like a pogo stick almost. So they had a sort of a canister attached to the spacecraft, and they brought the whole spacecraft even closer to the surface until it touched and injected material inside. So their sample collection device was very, very different than ours. It was not designed to collect as much sample as ours. And so they have collected less material, and they are now back. They left Ryugu, that's the asteroid they went to, while we were still at Bennu, and their sample came back in December of this past year. So they've been looking at it. They're just now starting to publish their first papers. So they got a few grams of material, and most of it is very small pieces, dust and sand particles. So their sampling mechanism was a bit different. And like I said, the scientific measurements they made were a bit different, although there is commonality and some overlap between the measurements they made and we made. And so we are working with that team. In fact, they have members on our team and we have members on their team who actually collaborate. And we're hoping to learn a lot more about both of these meteorites by comparing them to each other and comparing their samples to each other.
Thank you so much. Unfortunately, this is the last question that we have time for, but I think that this is a really good one. If any of us were to travel to Utah in September of 2023, is there a location that we could observe the spacecraft returning to Earth?
I expect, that's a good question. I don't know off the top of my head how big the Utah Test and Training Range is. But it might be possible. I mean, I expect that the capsule coming through the atmosphere is going to leave a trail. So I expect it would be visible. if you can get close enough. Unfortunately, I don't know how close you can get, but I bet actually you could deduce that as well as I could just by, whipping up your Google Maps.
Well, that was really
that's the last
great. That was really, really awesome, Dr. Hamilton. What a great presentation. And you're right, those are some really great questions. And thanks for giving a shout out to my math there, the linear algebra. I appreciate it. So, all right, so if everybody will clap, and you can unmute and say thank you and extend your appreciation to Dr. Hamilton spending part of her day with us.
Thanks to all of you too.
Thank you.
You guys
That
have
was really
asked me.
fabulous.
Thank you so much.
Thank you so much.
Thank you so much.
Thank you.